This video will cover a very specific kind of improper integral of type 1, which is called the p integral. And so that is this guy right here. That is the p integral, the integral from 1 to infinity of x, 1 over x to the p for, I guess, its power, 1 over x to the p dx. And so the proposition is that this integral converges if p is greater than 1, and diverges if p is less than or equal to 1. So we are going to prove that, and we're going to do that by looking at the three cases separately. P is greater than 1, p is less than 1, or p is equal to 1. Those are the only three possibilities. So if we examine those three, and we can put the answers together and get our conclusion. So let's start at by looking at p is greater than 1. So we have the integral from 1 to infinity of 1 over x to the p dx. As the definition of improper integrals tells us, this is the limit as t goes to infinity of the integral from 1 to t. I've written this as x to the minus p. X to the minus p to emphasize that we are doing a power rule. And so when we take the antiderivative, we add 1 and we divide by the new power. So there is the antiderivative that we are going to use to evaluate from 1 to t to use FTC2. So I want us to take a notice here. We are in the case where p is greater than 1. And if p is greater than 1, then 1 minus p, which is the same thing as minus p plus 1, which is our power up here. If p is greater than 1, then that is negative. That is negative. So if I move that downstairs, if I move the exponent downstairs, right, then I get p minus 1, and that is a positive number. So that is what has gone on here. I've taken the 1 over 1 minus p outside. We still have the limit. We've done the top, which has given us t to the p minus 1, which is the power, now that I've moved it into the denominator, to the positive power, minus 1 over 1, which is just 1. So we are letting t go to infinity, so this 1 over p is staying on the outside. We have 1 over infinity, right? This is a thought process. We have 1 over infinity to a positive power in the denominator, which is going to 0. So 1 over 1 minus p times 0 minus 1, which is multiplying by minus 1, gives me 1 over p minus 1, which means the limit exists, and so the integral is convergent. That is the first case where p is greater than 1. Let us look at the second case when p is less than 1. So we are going to have the exact same steps here, the same antiderivative. It's still the power rule. But now, if p is less than 1, then 1 minus p is already positive. This is a positive power. So if we leave that upstairs, again, I pull out the denominator, I pull out the constant, and I do the FTC part 2, right? So we are doing the top value minus the bottom value. So t to the 1 minus p minus 1. That now is, as t is going to infinity, here's my thought process, that is infinity to a positive power, because that power was already positive in the numerator. The previous case, I had to bring it down to the denominator to make it positive, but it is already positive in the numerator here. So if this is growing towards infinity, then my answer is going to be infinite. In other words, the limit does not exist. And if the limit does not exist, the integral is divergent. The integral is divergent. So we have one case left. We've done p is greater than 1. We've done p is less than 1. The last case to examine is when p is equal to 1. And so that means that integral becomes, if I put p equals to 1, I get this, the integral from 1 to infinity of 1 over x dx. 1 over x is the power of x that does not work with the power rule. The antiderivative that is going to be used, or the correct antiderivative, is the logarithm. the ln of the absolute value of x as t is going to infinity. We have this ln of absolute value of x from 1 to t. Plug this in. Plug this in. So you get ln of t minus ln of 1. Ln of 1 is 0. The limit as t goes to infinity is the ln of infinity. The ln of infinity, which we had seen in a previous video, and you should have seen in Cal 1, as the logarithm graph goes to infinity. As x goes to infinity, the logarithm also grows. Slowly, mind you, but it grows to infinity. And so that limit does not exist, and the integral is divergent again. So we had divergent here, convergent there. Put those all together, and we have the integral from 1 to infinity of 1 over x to the p dx converges, that was our first case, when p is greater than 1, and diverges in the other two cases, which can be combined into p is less than or equal to 1. Let's do a couple of very quick examples here without integrating. We want to decide if the following integrals converge or diverge. I don't need their value. I'm not asked for their value. All I'm asked is, do they converge or diverge? So let's look at the first one, the integral from 1 to infinity of this 1 over the square root of x dx. Well, this one, the square root of x is x to the 1/2, which means that our power of p, right, this power right here, our power of p is 1/2. That is less than 1. And so without integrating, I know immediately that that integral is going to diverge. The second one, so we have the integral from 1 to infinity of x to the pi over e dx. So pi over e, that is our power p. Pi over e is greater than 1. And if it is greater than 1, the proposition tells us that the integral converges. And that's it. Without integrating, we know the behavior, not necessarily the value in the convergent case, but we know the behavior of those integrals. And this p integral is going to be important for an application which will come later, which is the p series.